Hey, good morning. Nice to see everyone. Thanks for joining. Today I'll be talking about the evolution of how companies are using data lakes and some practices for monitoring your data lake. Is this better? And as you're running production loads on it, that you can be sure that things are working. So thanks, Pete, for the intro. My name is Paul Lapis. I'm the CEO of a company called Intermix, and we provide a dashboard for data engineers to keep an eye on their mission-critical data flows. This talk is informed by our experience working with a number of innovative companies who are our customers, as well as ourselves. We run a pretty large-scale data platform for processing and analyzing data as well. And so, to win in today's market, companies must build core competencies in leveraging data. This is no surprise to any of us here. Data-first companies are dominating their industries, and we hear mentions of AI in earnings calls, and all over the place when companies talk about how they think about competing in the market. The category winners within each category all share common characteristics. They're really good at collecting data. They typically collect unique and proprietary data within their particular vertical. They're really good at processing that data at scale and deriving insights from it. And then finally, they've been able to accumulate the best people, data engineers, data scientists, data analysts, in order to make use of that data. And these are some of the customers that we work with. And don't take our word for it. These are the companies that are winning in their own markets and doing some very interesting things with data. So these trends in leveraging data to compete and to win in your category have led to a shift in how companies think about building out their data platforms. And the shift is away from vertically integrated products. These are the mix panels, the amplitudes of the world, where data integration, processing, and dashboards all sort of were delivered as one thing, after that, monolithic data warehouses, where all data was stored within the data warehouse, to data lake-based architectures. So in a data lake, traditional concepts of ETL are being reimagined for a new world where you have source data residing in different clouds, third-party vendors, third-party applications. You have enormous volumes of data. You have terabytes of new data arriving in all different formats every single day, with the expectation that it'll be stored forever, and the expectation that your data scientists can access it forever, very quickly, and apply their algorithms to where it lives. And then, you also have rising workloads due to demands of machine learning. Companies want to leverage machine learning and algorithms to derive insights from that data, as well as the democratization of data, where everybody in your company essentially wants their own dashboard. Data lakes, what we've seen, data lakes, though, all share common characteristics. There's an object store, like S3, where raw and unstructured data is being stored forever. Number two is you've got several analytical databases or query processing engines that operate on that data and warehouse it. And then finally, you have an orchestration layer that coordinates how data flows through those various databases to implement the various processing requirements for the various models that you're putting into production. So, what we have seen in our experience is that the adoption of data lake and data lake initiatives have accelerated significantly in the past 12 months. It's been pretty quick. And we think this is happening now, quickly for three reasons. S3, if you're talking about Amazon Web Services, S3 is the cheapest possible place to store your data forever. And really, there's a trade-off between speed and cost. And so you only want to pay for fast queries when you need fast queries. So you may as well just store everything in S3. Number two is that one of the biggest challenges of processing data at scale is data movement. Getting data from one place to another sometimes isn't possible. Oftentimes it takes a lot longer. It might take hours in order to get data from one place to another. Leveraging the in-house capabilities of your various databases is more and more important to bring your algorithms into the database where the data already sits, or into the area where the data already sits, so that you don't have to move the data around. So there's the best tool for the job, and you want to be able to use that tool without moving data. And the number of tools are also proliferating. And then finally, you've got different audiences, right? As your company grows and demand for data grows within your organization, your data scientists versus your data engineers versus business analysts all want to interact with the data in different ways, using different programming languages and different tools. And so that has led to a need to support various interfaces and systems on these data lakes. So let's sort of make it real for a second. I wanted to share a common pattern tech stack that we are seeing emerge with the companies that we work with and the companies that we talk to. And at the very basic level, there's an object store, there's S3, and we think about workloads in two categories: batch workloads, where you're continuously running the same job on a data set to move it along, to implement a model, and then your interactive use cases. A warehouse is used most often to store aggregated and pre-processed data. That is, the main source, usually for business analysts and others to connect to. We see Amazon Redshift as being really, one of the biggest and most popular. It's being used for both interactive and batch use cases. Hadoop and EMR is increasingly being used for batch use cases to largely, as the first stage in a data pipeline. It's really good at processing very long tables, at aggregating very, very high amounts of, large amounts of events. And so we see Spark SQL, Scala, and Python being implemented on top of EMR in order to implement pipeline stages where you just don't want to store that raw data in a data warehouse. It's just too expensive and takes too long. We see Presto accelerating in popularity, or Athena, which is the Amazon service that uses Presto on the back end. Presto is becoming very popular in the companies that we work with because you can access the data where it lives. You don't have to move data to actually query it, and you're able to join data from different data sets with one single statement. So it's pretty slow in some cases because of the way that it's implemented, but it's very, very useful for interactive use cases. And then finally, there's an orchestration layer that will manage the task of storing your jobs, your batch jobs, and then executing them within a DAG to implement your various models. The technology that we see gaining more traction in the open source world is Apache Airflow. And so, we see this so much, we've given it a name. We call it the pair stack. Let me just sort of pause for a second and see a show of hands. How many people in this room are using at least one of these technologies at the moment? Cool, and then keep your hands up if you're using all of them. All right, so cool. All right, so there's some adoption of these technologies here as well. So let me talk about how the stack is being used. So unlike end user applications, data apps run jobs on this stack. There's three categories of data apps. The first being data integration services. This is vendors and tools that move application raw data into your data lake from external systems. Number two is analysis tools that connect to your data warehouse or connect to any of the systems in this stack to to analyze data and get data out. And then finally, there's workflow orchestration that we just talked about. These are systems that implement workflows. Now, monitoring the performance of these data applications is just as critical. If data is important to your business, and if you are working on data projects where the reliability and performance of data is important, then monitoring the performance of these data applications is critical to making sure that, that things are working well. And so that's what we're going to talk about next. So the fundamental problem, that we're solving as data engineers is to ensure that the data pipelines are working, right? To ensure that the models that we're implementing, that we're processing within these data lakes is working. So we want to answer questions like, are data flows operating normally? Are data apps able to access data? What is the service level of the users and the applications that are actually running queries on these systems? And what are my cost drivers, right? What am I spending for all of this technology? And how do I think about attributing the cost of this technology to the various teams and users that are using it? This stuff is getting more and more expensive as you're storing more and more data. In order to accomplish this, you need new types of metrics. Traditional metrics like network utilization, CPU utilization are more or less irrelevant when you're thinking about monitoring data lakes, because you're not monitoring network packets, you're monitoring how an individual event will flow through your system and be processed and aggregated as it flows from its source to its destination. So any system where you're going to keep an eye on what's happening in the data lake must consider new types of data. Number one is you need to actually understand what the jobs are that are being run, the syntax and actual text of the SQL queries that are running, as well as performance characteristics of those queries themselves. Whatever database they ran in, you want to understand what was the performance of that query, what were the resources used for that query, and then were there any issues related to that. Number two is, in our experience, our customers run about 2 million queries every week on these systems, some more, and that's a lot of queries. And typically there's dozens of applications that are running queries, and understanding which application is running what query so that you can map the context of that user in the application that's running the query down to how well it executed when you're talking about running a model across multiple databases is really hard. So you need some way to associate who ran that job back up to the end user of the data application. And we'll talk about one approach to doing that. And then finally, because your jobs are operating on data, this could be data within a relational database, it could be a partition within a Hive metastore, it could be any data set that is being queried or accessed. You also need to trend and track the size and the characteristics of the underlying data store that is being operated on, because oftentimes changes in the structure of that data or how the data is laid out impact the performance of the jobs that are querying it. So for example, if you're in Redshift and you're querying a table and that table is growing very quickly in number of rows, the queries that are scanning it are going to get slower. If you're running a Spark SQL job on top of S3 and the layout of your, say that you're using, sort of using Parquet and you've selected the wrong partition scheme for S3, then that query is going to run really, really slowly. So you need to be able to understand how those things are linked together and to be able to link what queries are running on what tables. So, if you're running production data and your company is relying on it, there's essentially 3 problems that you want to solve. I talked about them here: cost, efficiency, and SLA, and I'll sort of dive into them a little bit. So service level agreement. Users of your data applications are not always part of your team. They're part of teams outside of your team, and so they expect a certain minimum level of service when they're accessing the data. So this involves query speed, this involves data freshness, This involves reliability of the actual data when it's being queried. And so really you need to know, am I meeting my SLA, right? What is the performance of these various users? How are these things trending over time? Is this particular model, the various jobs that implement this model, are they getting slower over time? Are they getting faster over time? Do you even know? What are the biggest bottlenecks if things start going wrong? What is the root cause of why things start going wrong? Efficiency is a big problem. What I mean is, when there's problems, how quickly can you isolate where the problem is and what's causing it? And do you know of problems before your users tell you? We hear oftentimes that users will complain about slow queries or inaccessible queries or the database is down or whatever. And what ends up happening is the folks that are responsible for the data stack now have to stop what they're doing and go off and troubleshoot and figure out what's wrong. But what if you had a system where you could be alerted automatically when things started going wrong and be able to pinpoint very, very quickly what the source of that problem was? So, why are my models slow? Why is this query failing? Where do I have contention issues, et cetera? Cost, we see, is becoming a bigger and bigger problem. Understanding what's driving the cost of this system will help you answer questions like, why are we spending so much? Are we oversubscribed in certain areas of the system? Are we undersubscribed? If we need to add resources somewhere, what's the best place to add resources? And how does that impact the performance of the models or the queries that we're running? And then finally, these problems that I just described, they get bigger over time, right? They don't get smaller. They get bigger as you add more workloads to the system. The demand for the data goes up. As you add more data sources. Third-party tools, I'm referring to tools like Segment, tools like Illuma, Fivetran, tools that are being used to move data into your system. Oftentimes, these jobs are written by third parties that don't work for your company, and so you kind of need to know what they're doing on the system to the extent that they might be running wasteful, expensive, and inefficient queries. That's like visibility that you need to have so that you're not surprised later by some action that was taken by them. So let's sort of dive into SLA. So here's some examples of data applications that we see growing in popularity across the 3 categories of applications that I talked about. Across data integration services, workflow orchestration, and the analysis tools. Now, I really recommend that you think about having a dashboard that contains data like this in your environment. It's not that trivial to build, but this is what I see as being something that will really help you keep an eye on really what's going on in your system. So across monitoring the performance of queries, ranking how things are changing over time, and then spotting issues very, very quickly is super important, right? So you want to have a dashboard that aggregates all this stuff for you in one place. So what is the average latency trended over time of my key workflows and my key models and my key users? How does my utilization of my various databases, storage, and database systems, how does that map to the performance of queries? We're running different apps on these systems and dashboards and models. It's very useful to know which ones are the most expensive, which ones are the slowest, so that you can go tackle those for optimization. Which of my users are the most wasteful? There's typically an 80-20 rule in most of these things, where 20% of your users and 20% of your jobs eat up 80% of your utilization and your resources. So understanding who and what those are is really useful. And then finally, 2 of the biggest problems that create issues in these data stacks is contention and then resource starvation. So contention could be queuing in Redshift or in Presto, where you've got a lot of jobs that are all aligning, that exceed the concurrency configuration for that particular database, that creates bottlenecks, or when you run out of resources, either disk space, utilization, you run out of you're starved for I/O or CPU in some database system. And then, where are my jobs failing? Where's the pipeline getting stuck? And which at sort of which stage is that happening? So I wanted to introduce a concept of a way to see into which app is running queries using query annotations. This is something that we're seeing more and more applications provide. Query annotations, essentially I'm talking about adding a comment to a SQL query that contains metadata about who ran that SQL query. This is a vendor agnostic way of adding context to a query to understand where it came from. So anything can be annotated, obviously. The name of the app, the user that was logged into the application that ran the app, which is really hard to see. The name of the task or the job or the DAG that's running. Another metadata that can help you sort of pinpoint who's actually running this job. So this can help you answer a lot of questions that you can't get just by looking at the jobs and the queries from the actual query engine itself, right? There's so many queries, it's impossible to actually carve it up without some way of annotating these jobs. So a number of dashboards include annotations now by default. Here are some examples. I'll let you deduce which is which. Some are better than others. If you do choose to add annotations in your own systems, use C-style comments, because if new lines get stripped from the SQL text when you're parsing it, then if you're using dash comments, you won't know when the comment ends and the SQL begins. And then use some structured format like JSON. If you're using Apache Airflow, here is an example schema that is very, very useful. And we've written, in our company, we have plugins, we support annotations in our product, and we've written a number of helper libraries and ways to add annotations using Python. So after this talk, if you want more information on using these, just get in touch with me and I'll sort of share some more information on that for you. Talking about efficiency, so quickly understanding where problems are and what the root cause of problems is what I wanted to talk about next. Do you ever wonder, is my query latency growing? Do I have issues on the system across my various databases? Are queries failing? Why are they failing? To illustrate how hard it is and important it is, I wanted to go through a troubleshooting scenario where, say, you have one of your models takes 10 minutes to run, say it takes 15 minutes to run, and all of a sudden it's slower by 20%. You wake up in the morning and all of a sudden this DAG is much slower than it was, and that's creating issues for you. So you're going through the 5 whys process. You ask, well, why is it slower? So I'm going to walk through sort of some of these 5 whys and then talk about, well, what are some of the metrics that we need in order to actually answer these questions. So my DAG is slower by 20%. Well, that's because one of the tasks within this DAG experienced a 4x latency spike. Okay, great. So I understand that latency of the entire model, DAG, was caused by this one task. Well, why did that one task slow down by 4x? Well, that's because one of the queries within that transaction went from 10 seconds to 3 minutes. So we can isolate within that task, well, which is the job that was taking longer. Why did that happen? Well, one of the tables that this query was scanning went from 10 million rows to 1 billion rows in less than a day. So all of a sudden, some tables started growing that caused this query to go slower. Okay, great. Why did that happen? Well, there was another query, query 123, that started inserting data into this table over the past day. And then who ran that query? Like where did that query come from? So we can see that query was run by an individual using Redash that was inserting data into this table. So very quickly we can isolate, okay, we know that there's a problem, and we can isolate it down to it being caused by this one query, this one job being run by this person named Jordan. And so we can only sort of stitch this data together if we're monitoring using the metrics that we talked about earlier, right? For step one, we need to understand the query latencies for certain DAGs and be able to know and to annotate those jobs so we can understand, well, which model are these queries a part of. The same thing with step two. To understand that a table was growing, we have to trend the size of a table and the row count of a table over time so that we can sort of track the growth of that. Step four, we need to understand for this query statement, it was inserting table into this, data into this particular table so that we can map those two things together. And then annotations, we'll use that again in order to actually figure out which data was inserting into it. This is a simplified example, but this kind of thing happens all the time across, we see it happening constantly across many different databases and systems. It would take somebody hours, if ever, to really diagnose that this was the cause of a particular model or query slowing down. But if you have this data at your fingertips, you can get the data much, you can actually isolate that much more quickly. So some advanced testing that I'm not going to talk about here, but I wanted to point out that we're seeing more and more people doing, that you should be doing some level of this in your environment, is data validation itself. Actually validating that the results of your aggregations are producing the correct results, and that as you're ETLing data from one source to a destination, that you're capturing all the rows. As some very, very simple examples, data validation is becoming a bigger problem as we're putting more things into production. And then anomaly detection, right? Like, how do I understand when the behavior of the system is changing? If I'm inserting 1,000 rows per day into this table and that goes down to 10, that probably is an indicator of an issue. So talking about cost, so there's a trade-off between how fast the query is and query speed and what that query costs to run. If you're querying S3 data that lives in S3 with Presto, that's pretty inexpensive. If you're querying it with Amazon Redshift, that's a lot more expensive because Redshift, storing data live in Redshift is more expensive than S3. So it's important for us to think about this in the context of all the various use cases and jobs running on the system. There's some queries that you don't want to pay a lot of money for, but sometimes adding, moving a particular workload to a different database will make it run much faster, but understanding what's driving those costs is super important. Why track query cost? You can make decisions on where to invest in order to speed things up. You can charge back to other departments in your company that are using these data platforms. Like you can, sales and marketing teams that are using half of your data processing engine, you might go get some budget for them. And then also, it'll help you sort of answer the question of what is it going to cost me to increase the recency of my data? If you want to move a table from being 1 day old or to being updated daily to being updated every 4 hours or every 1 hour, there's a huge cost to that because it means you have to run more jobs on the system in order to speed up the recency, and that doesn't grow linearly. Adding, quadrupling the number of jobs in the system doesn't mean that your cost will go up by 4x. It might mean that it'll go up by a lot more than that. So understanding what those drivers are is super, super important. One pattern that we see a lot is the shift that we were seeing away from monolithic data warehouses to data lakes, where all raw data used to be stored in Redshift and now it's just being stored in S3. And one of the big use cases we see is sort of moving raw data processing out of Redshift and into Hadoop. So if you have, if you're processing, say, for example, mobile events and you're getting, 100 million events a day, then aggregating that down to a 5-minute window is really easy in Hadoop. It's much more expensive and hard to do in Redshift. And so those are some of the first workloads that we're seeing move off And if you do that, you'll end up being able to reduce a lot of nodes in your Redshift cluster because you won't need to have it to any as much storage online. So you can delete nodes. Measuring cost of a query is hard because different databases or different query engines are different. They have different cost drivers. A few examples. In Amazon Redshift, the cost driver is the number of nodes that you have in your cluster. And so the metrics that you need to track for a query are different. You need to know how many rows it's scanning or how much memory it's using so that you can help to figure out what is the relative expense of this query over another query. In Amazon Athena, your cost driver is just your S3 storage. And so there what you need to track is how many bytes are being processed by this particular query, or how many columns are being accessed by it, which will drive up the number of bytes. In Presto, your cost driver is more complicated because Presto uses databases as its catalog, and so you need to sum the cost of the various queries on each of the databases that Presto is accessing, in addition to the internal handling of that statement within the Presto workers themselves. And so tracking that is much more complicated. And so, tracking metrics for each of these queries within each database is really, really important. So that's it. I wanted to introduce you, or to offer, we have a weekly newsletter that goes out to about 5,000 people with really high open rates. If you have any content that you're publishing or blog posts that you've written, we would be more than happy to distribute that into our newsletter that goes out weekly. Just email submissions at sfdata.io, and then we'll get it in there. It's a really great community of data engineers. So that's it. Thank you very much.